Hey everyone, this is it, last lecture of Math 143, so let's get started. And I just want to remind you, right, we've been talking about vector-valued functions, parameterized curves, and so we want to think of a parameterized curve as the path of some particle in space, and so if r of t is the position of a particle at time t, then when we compute the derivative, right, that's going to be the change in position. What do we call change in position? It's velocity. And of course now, velocity is a vector, right? Not only do we want to know how fast it's going, that's the speed, we also want to know in what direction you're traveling, right? So velocity, it would make sense, velocity is a vector. So then r prime of t, which we will write as v of t, is velocity. And if you take the derivative of velocity, so change in velocity, that's acceleration, that's the second derivative of position. So r double prime of t, that's going to be v prime of t, which we write as a of t, is acceleration. Okay, and once again, acceleration is a vector as well, right? It's the derivative of the velocity vector. Oh, one last thing. So we'll say also, the magnitude or the length of velocity, this is what we call speed. So this is the speed, right? So velocity has both speed, that's the magnitude, and the direction. So let's do some examples now. So suppose that acceleration, so a of t, is, now your book goes back and forth between IJK and angle bracket notation when they're talking about this. I'm going to just stick with angle bracket notation today. I like the math approach better than the physics approach, but you should be able to go back and forth between angle bracket and IJK notation in the book and especially in your physics classes. So let's say that the acceleration is 2t, 1, 0. So suppose we know the acceleration and then we also know the position at time 0. So r of 0 is 1 minus 1, 1. And we also know the velocity at time 0. That's going to be 2, 0, 1. And what we want to do, so first of all, I would like to find, so this is going to be part A. So part A, find r of t, and part B, I want to compute the speed at t equals 2. So find the speed at t equals 2. All right. Well, okay, so we're given acceleration. We need to find position. That means that remember, acceleration is two derivatives from r of t, so we need to work backwards by taking two antiderivatives to get from acceleration to position. So for part A, v of t is going to be the antiderivative of a of t. So if we take the antiderivative here, what we're going to get is t squared plus some constant, let's call it c1. Then we're going to get t, the antiderivative of 1 is t plus a constant, and then the antiderivative of 0 is a constant, call that c3. Okay, so our velocity vector has to be of this form right here when I take the antiderivative, and now I need to figure out who C1, C2, and C3 are, and I can use that by knowing the initial velocity, right? So what we have is 2, 0, 1. That is V of 0. And V of 0, if I plug 0 in over here, what we get is C1, C2, C3. So this allows us to solve for our constants of integration and get our velocity in final form by substituting for C1, C2, C3. All right, so now we've got V of t equals, so it'll be t squared plus c1, which is 2. So t squared plus 2, comma, t plus c2, c2 is 0, so that'll be t. And then c3 is just 1. Right? So there is our velocity vector. Now we need to take one more antiderivative to get our position. So r of t is going to be the antiderivative of v of t. And so if we take the antiderivative, we will get a t cubed over 3 plus 2t plus some constant, let's call it d1. And then t squared over 2 plus d2 and t plus d3. Once again, I need to find these constants of integration, and because I know r of 0, we can do that. And so now we have 1 minus 1, 1. That's r of 0. And if we substitute 0 in here, that'll give us d1, d2, d3. So r of t is going to be t cubed over 3 plus 2t plus 1. d1 is 1. And then d2 is negative 1, so that'll be a t squared over 2 minus 1. And then d3 is positive 1, so that'll be a t plus 1. Now, for part B, all right, so there's the answer for part A. For part B, so we wanted the speed when t equals 2. So let's come back, and we know what v of 2 is, right? We take v of t and substitute 2, and what we get is angle bracket 6, substitute 2, 6, 2, 1. So the speed, that's the magnitude or the length of the velocity vector, that's going to be square root of 36 plus 4 is 40 plus 1, so square root of 41. Okay, so there's the speed. Let's try another example here. So a particle travels along a curve who has parameterization r of t equals 3t squared plus 1, 3t squared plus 1, comma, t cubed, comma, minus t. T cubed, comma, minus t. So at time t equals 2, right? So we have this particle traveling along a curve that's given by this parameterization. At time t equals 2, the particle deviates from its path in the direction of its tangent line. Or I guess I should say in the direction of its velocity vector is probably better. At what point will the particle be at 3 seconds later. So 3 seconds after it deviates from its original path. So here's the idea. I don't know what this curve looks like, right? But it's got some shape like that. And then let's say here we are. Let's say this corresponds to time t equals 2. What happens? So the particle is traveling along this curve. All of a sudden, it slips off in the direction of its velocity vector. And so now the question is, at what point will it be 3 seconds after that? So here's the idea. If I could find the equation of the line, right, if we could find a parameterization of the tangent line, then we could just plug t equals 3 in there, and that'll tell us what this point is. So first I need to know what that point is, right? So when t equals 2, this point is going to be 13, 8, minus 2. So I'm looking for the line that passes through the point 13, 8, minus 2 that has velocity, that has tangent vector equal to, or has direction vector equal to the velocity vector. So v of 2, oh, I guess I need to compute the velocity first. So v of t is equal to 6t, 8t squared, and minus 1. So v of 2 is going to be, oh, I don't know where I got 8t squared. That's 3t squared. So v of 2, plug a 2 in here, I get a 12, then I get a 12, and then I get a minus 1. So there's the velocity vector, right? That vector right there. So now the parametric equations for the tangent line are going to be x equals 13 plus 12t. Y equals 8 plus 12t. Z equals minus 2 minus t. So at time equals 0, we're right here. At time equals 1, we are one copy of the velocity vector. At time equals 2, we're here. At time equals 3, we're here. And so if I plug 3 in, that's going to tell us what this point is. So let's plug 3 into the parametric equation, t equals 3 into this parametric equations. And so this is going to be, for t equals 3, we will have 13 plus 36. So that point is 49, the x-coordinate. And then we'll have 8 plus t equals 3, so 36, so that's 44. And then t equals 3, that'll be a minus 5 right there. Right? So that point is exactly where, if it slips off that curve at t equals 2, then 3 seconds later it's going to be at 49, 44, 5, or minus 5. I don't want to do a whole lot of physics, but we'll do a little bit of physics here. So you just need to remember, so Newton's law, so Newton's second law. Goes like this. If a force, let's say f of t, so this is going to be a boldface. Remember, force is a vector, so this will be the force at time t, acts on an object of mass m, so acts on an object of mass m to produce acceleration a of t, then, right, so what does Newton's second law say? F equals ma, right? Force equals mass times acceleration. And I just want to do one application of this. In your book, you'll see a bunch of applications. We're just going to cover one of them, and that's the projectile motion. So application. Projectile motion. And so here's the idea, what I'd like to do, and we're just going to do it in 2 dimensions here. So the force due to gravity is, so gravity just goes down, right? So there's no x component. So it's 0, comma, negative gm, right? Where g is the gravitational constant. So where g equals, well, it's approximately equal to 9.8. So then, according to Newton's second law, what we have is, so mass times acceleration is equal to the force right here, which is 0, comma, minus gm, which tells us then the acceleration due to gravity is 0, comma, minus g. All right, so viewed as a vector, we're just thinking in 2 dimensions now, right? Here's the acceleration due to gravity. So now, suppose a projectile is fired at an angle theta with, let's say, initial speed v0. So an angle theta with initial speed v sub 0. Right, so here's the idea. Think of a projectile, an arrow, or a bullet, or a ball, or whatever. Right, so we measure theta from the horizontal, and then, so this would be our velocity vector, initial velocity vector. Right, and so the length of this vector is v sub 0. Okay, so fine, so then v of 0 is equal to, just do a little bit of trig, what we get is this is going to be v0 cosine theta, comma, v0 sine theta. Also, I mean, we don't have to do it from the origin, but I just want to think of, for now, our starting point, the place where we fire it from. Think of it as the origin. And so to simplify things, let's go with, right, our initial position equal to the vector 0, 0, so we're starting at the origin. Okay, so now, I just erased my, sorry, I erased my acceleration. I just want to keep that in there. So a of t, remember that was 0 minus g. So that tells us that if I want to know what v of t is, by taking the antiderivative, we get constant c1 in the first entry and minus gt plus c2 in the second entry. And then v0 we know is this. That tells us that c1, if you just solve, right? c1 is this part, c2 is that part right there. So that will be equal to v0 cosine theta, comma, minus gt plus v0 sine theta. So there's our velocity. And if I take one more antiderivative, so r of t, that's going to be v0 cosine theta times t minus gt squared over 2 plus v0. Sorry, I forgot my constant of integration. Plus d1, comma, minus gt squared over 2 plus v0 sine theta times t plus d2. Of course, since I chose r0 equal to 0, 0, that's going to tell us that d1 is 0 and d2 is 0. So, final form, right, once you solve for d0, d1 and d2, what you get is v0 cosine theta t, comma, minus gt squared over 2 plus v0 sine theta times t. Right? So this right there gives us everything we need to know about projectile motion, assuming that we started at the origin, and of course we're ignoring air resistance or anything else. So gravity is the only force that's operating here. So let's just try one example. An arrow is fired at an angle of 30 degrees and speed 20 meters per second. And the question is, how far does this arrow travel? Maybe I should word this better. How far away does it land? So I don't want to know how far the curve is that it travels. I want to know how far in the x direction. So how far away does the arrow land? Okay, so to solve this, we're just going to make use of this equation right here. So what we have is r of t is equal to, so let's see, v0 is 20, theta is 30 degrees, so cosine of 30 is root 2 over 2, so this will be a 10, root 3 over 2, so that'll be a 10 root 3 times t, so 10 root 3 t in the first entry. G is 9.8, so that'll be a negative 4.9 t squared plus sine of 30 is 1/2, so it'll be 20 times 1/2, so 10t plus 10t. Now, let's see, we want to know how far away does it travel, or how far away does it land? And so what does it correspond to when it lands? It tells us that the height is 0, so we need the second component equal to 0. If we can find the t value for which we get 0 here, we could plug that t value into this side right here, the x side, and that'll tell us the x position, the x coordinate, right when t equals, or when t gives us the landing time, or when t equals the landing time. Okay, so first thing we do is we solve minus 4.9 t squared plus 10t equals 0. And so that's going to tell us, if we factor out a t, we'll get negative 4.9 t plus 10 equals 0. T equals 0 is not the one we want. We want this one here. So t equals 10 over 4.9. It's about 2. It's a little more than 2. It's 2.04. So 2.04 seconds. All right, so if you shoot an arrow at an angle of 30 degrees, speed 20 meters per second, 2.04 seconds later, it's going to hit the ground. So now, total distance, right? So distance in the x direction, of course, that's going to be 10 root 3 times 2.04, which comes out to be about 34.6 meters. And something's funny in my notes. Let me just check that on my calculator real quick, because I think I only plugged in, yeah, hold on, here, so 10 times square root of 3 times 2.04. Oh, sorry, yeah, 35.3 is actually what it comes out to be. 35.3. So if you shoot an arrow like that, right, it's going to travel along a path. Eventually it's going to hit the ground. So if it was an angle of 30 and this was 20 meters per second in speed, right, then this distance right here will be 35.3 meters. Okay, well, you survived. Other than the final, you survived Math 143. I wish we could be seeing each other in person, but obviously we weren't able to. So hopefully at least learned something and enjoyed this class. We will see you on Friday to review. And then your final exam, depending on which section, your final exam is either on Monday or on Friday. All right, so we'll see you later.